TranSpec's ability to correlate to properties opens up a wide range of qualifying applications of materials. Mechanical properties could be predicted, as spectral information can relate to properties such as mechanical strength and melt flow index, reducing the need for time-consuming measurements such as DMA. Fire performance can also be correlated to flame retardant concentration and polymer matrix, reducing the amount of UL flame tests required, for example. Colour can also be measured in wide wavelength TranSpec, and this can be used to both colour match but also aging issues in qualifying materials. In this example, concentrations of alumina trihydrate and alumina trihydroxide in EVA give varying LOI scores. This can be correlated by TranSpec to the spectral data and models built to predict LOI. Again, this is a unique feature of TranSpec. In this example, concentrations of alumina trihydrate and alumina trihydroxide in EVA give varying LOI scores. This can be correlated by TranSpec software to the spectral data and models built to predict the LOI. The first step involved successfully building a model on the concentration of the additive in polymer. The regression coefficient then showed the LOI having a positive correlation with the additive and a negative with the polymer, which is logical. Again, this is a unique feature of TranSpec, an instrument that in a single measurement uses a model that can measure both FR content and also LOI for the material. These types of multiple measurements can be built quite rapidly, as the same spectral data and manipulation of the data can be used to link all the entered properties of interest. There may also be times when you want to use TranSpec as a research tool to discover how material properties change over time. In the following case, a client wanted to find out what was happening to their materials under various time and temperature conditions, and then be able to predict the history. Wide wavelength TranSpec was used for temperature aging measurements on some epoxy resins with glass mat systems used for insulated materials in the power industry. A method was required to track their time and temperature history. Wide wavelength was used as analysis time takes between 4 seconds, and it covers the UV vis to NIR region. The materials were aged between 100 and 200 degrees for up to 28 days. Here we can see an overlay of the spectral data and can see that both colour changes and molecular degradation can be tracked. The software can correlate this to give measurement models, and this can then be used rapidly by anyone to give on-site measurements in seconds. The molecular peak shifts during degradation can be related to the carbonyl and carboxylic acid peaks. This is given information to what is happening in the degradation steps, and again is increasing in knowledge. The graph above shows a regression which shows the area of the spectra that are contributing most to the measurement properties. Here the colour region and carboxylic acid region is related to the days of aging at 160 degrees. The plot below shows the model prediction against actual values. The correlation is very good. Interestingly, TranSpec picked out different correlations for aging at 100 degrees where no colour changes occurred. Again, increasing knowledge. The graph above shows two different principal component representations of the epoxy material data. It shows the breakup into temperature families. From this we can measure the temperature regime, and then from there the time the material has been aged for. This shows the essence of a Simca model. It decides which population, in this case temperature, the sample falls into, on the basis of the chemistry through the regression coefficient. And then it validates it, and then it predicts the exposure time. Once it identifies the best model for the sample, it can then make its measurement. The conclusion from this type of research and development material assessment application gave a number of useful conclusions. That wide wavelength could be used to assess the quality of electrical insulation material. These epoxy-filled insulation materials can be correlated to time of degradation at fixed temperatures, or a time and temperature independently, and the calibration models provide excellent predictions. This gives information on what type of chemistries are going on in degradation, as well as ways of tracking them. This approach could be used on a variety of materials. TranSpec has found a range of applications in asset management through material assessment, and in this next example we turn to TranSpec Raman. TranSpec's unique ability to find correlations with performance and properties to give specific predictions to conditions is of interest for applications such as lifetime predictions. These are usually based around brittleness, molecular weight and chemical degradation, and also relationships with time and temperature history. Again, another key benefit is that it's a non-destructive technique and can be used on complex in-use objects. In this application, a polycarbonate part for the power industry was investigated. There was an issue where the part became brittle and would break over the lifetime, causing issues. A method for predicting the condition was required, and it needed to be non-destructive. A simple method was set up where good and bad samples were collected, and the properties linked to the glass transition measurements to the Raman spectra. In the plots above we can see the Raman spectra compared to the glass transitions, where there was a noticeable shift between good and bad samples. This was due to the physical aging. The glass transition values were then regressed to the spectra, and a model was built to predict both the glass transition and then the condition. The model now built has allowed the client to take a portable instrument out into the field to measure device in use and predict the lifetime and whether a replacement is required, something that was otherwise impossible. Behind TranSpec's measurements are the calibration models. TranSpec does not work ab initio. This is because it is looking for small variations in the material spectra and looking to correlate this to the properties of interest. Thus any models must be built specific to the materials to make them as accurate as possible. The model should ideally cover the full range of expected values and have enough intermediate values to validate the calibration, typically around 5 samples. This model building step can be carried out by the client using the supplied TranSchem software, but notice also offers a support package for clients who would like us to build the models for them. For TranSpec to make these types of measurement, we must first build the models. This requires a known calibration set, typically a range of concentrations of a formulation of interest. These are then scanned and the information such as concentration and properties can easily be entered. The spectra are then compared and a calibration model is produced through the software. For TranSpec to accurately measure your materials, the calibration model must have the additive or the property of interest in the polymer matrix. Extra additives in the sample, but not in the calibration model, will need validating to check if the model still fits before making the measurement. The detection limit for the concentration of additive starts at around 0.1%, but this will be material dependent. Multiple additives can be present in the calibration, and all of them can be modelled if required, and these models can be continually added to adapt and to be able to handle different pigments and additives. For materials that contain carbon black that have previously been tricky to measure, there is now a specific black material setup. The models will become more accurate and robust as more data is entered into them. Thus, as more samples are added, a legacy value is gained. The database can also be built from historic samples or as part of a formulations development program, so that building a model requires as little resource as possible. If you have a specific material of interest that you would like to test with TranSpec, then we do offer a proving service. We require 5 or 6 known sample materials to build the model, typically a concentration range of an additive. We then build and calibrate TranSpec to this and then test it on a supplied mystery sample and report this back to you so you can build confidence in TranSpec with your materials. If you are interested in using this offer, then please feel free to contact me after the webinar. We also offer a more general consultancy service to the plastics industry. This can be for TranSpec related property assessments and new applications, to more general analytical services and problem solving, as well as materials research and development. So if you have a materials based problem, then please feel free to contact our team and we can put together a specific solution package. To conclude this webinar, I'd like to recap on what we have learnt today. TranSpec is an instrument that allows for rapid, portable analysis through high-quality Raman or wide wavelength spectroscopy. The data can be correlated through TranSpec software to a wide range of metrics to give a tool that can tackle a wide range of requirements. Methods can be applied through quality control and quality assurance processes, can be used in research and development applications, as well as general problem solving issues, and also tackle a variety of in-use or end-of-life qualifications. Databases can be built from historic samples or as part of a formulation development program. And trials are available to build models for your specific materials, and this is a good next step to get you to see the many benefits of TranSpec to your materials. Thank you for listening. Now is your opportunity to ask any questions you may have. Please type them into the Questions tab on the GoToWebinar box on the right of your screen.